All right. Okay, so let's get started. If it becomes too loud outside, we can close the door. Otherwise, it's really hot in here. So I prefer leave it open for now. But we can see if we need to change. Okay. Okay, so first of all, midterm is coming Monday evening, and the scope. Right, the scope of midterm will be. I will send an email about this as well. But chapter 1, 2, 3, 4, and 5.1 and 0.2. Okay. So let me still close it. The scope of midterm is chapters 1 through 4, and then also section 5.1 and 5.2. Okay. So today we're going to finish this and start 5.3, but that's not included in the midterm. Okay. So pretty much all of the one parameter models, that includes beta binomial, gamma Poisson, and gamma exponential. Okay. And also actually in the normal model that we're doing, this normal. Okay. And then Monte Carlo approximation. Okay, great. So the exam will be written for like an hour and a half, but the room is good for 3 hours, and you can take however long you want. So I will send an email as well, and you're allowed to bring a double-sided cheat sheet prepared by yourself and a calculator. Okay, and so that's for the written part, and I will do a take-home part, but it wouldn't be too long, and I'll give you about like 24 hours to do it. Okay, so you're just gonna submit it either through email or to my office. Yeah. Right. So the plan. Okay. So so next Friday is the drop and our deadline. So that's what I want to meet for like returning the graded exams to everyone. So the plan is the midterm gonna be Monday evening, and then once you did the take home. Once you do the in-class written portion, I will give you the take-home. And I was planning to have it, you can email it to me, that might be easier, like by midnight Tuesday, like 24 hours, I mean, yeah. And then you can send it to me so I can grade it, and then Wednesday class time, I can return it. Does that work? So I'm talking about Monday, yeah. Yeah. So okay. So maybe let's see. I was thinking. So I mean, I actually don't. Whichever is fine. I was planning to have the midterm in class, like the written midterm, and then you can take the take-home part with you, and then you can do it, and then do it for like 24 hours, and then submit it to me by I don't know, like 11:59 Tuesday, something like that. Then I would get the time to grade it on Wednesday morning. Yeah. But again, I guess depends on people's schedule. So okay, I will make 2 options in that case. I can either, so if you want to take the 24 hours doing Monday, like for the Monday to Tuesday, like during the day, then you can take it for, oh my God, what I'm saying. I'm just trying to make sure that everybody has the equal amount of time to do it. And then I understand everybody has other midterms and class and et cetera. So I will say that in the email, whichever you choose. But no matter what, it's going to be 24 hours take home, and it's going to mostly be done with some of the questions. Okay. Yeah. All right. Yeah. Okay. Anything else about the midterm? Okay, if you need to reschedule, like because of the time, email me as soon as possible. Also with the AEO office, if you need any kind of accommodation, you should email me soon so we can see what we can do. Okay? All right, cool. So if no question, I think we will start talking about the material. So last time we were somewhere, let's see. Okay, pretty much, okay. So here, we were around this place when we ended, but there are certain things I want to restate. So let's maybe go back, sorry. Okay, so this is the model setup that we did, and then we recognize what are the sufficient statistics, but this is only working on the likelihood, okay? So this is only about the likelihood, and you need to make sure that you know how to derive and then get the joint. And then for those of you who have done mathematical statistics before, you know that, okay, with the likelihood, you come up with the sufficient statistics, and then you can do the maximum likelihood estimator from there. So for both Bayesian methods and frequentist methods, likelihood is always there. So you need to make sure that you know for the normal case, this is what you have. And going from there, we started to think about, okay, if we assume that we know the variance, sigma square is known, and we only need to make inference about the mean, theta, so a class of conjugate prior for the one parameter normal model is normal. Okay, so here again, we're using this term one parameter normal to refer unknown mean and known variance. Okay. Okay. Later, when we talk about two parameter model for the normal, it's both of these are unknown. Okay. All right. Cool. So with that, we started talking about, okay, since now sigma squared is given, we will talk about it, how you can like make that known once we get to the text example about the mid wind length. But here, in order to keep consistent, I even just write the prior theta conditioning on sigma square, meaning that it's given. So even though in the prior normal distribution, sigma square is not appearing anywhere, but we're trying to use this notation to be consistent, because later, once we start writing the posterior, you realize that the posterior is conditioning on the fact that you know about sigma square. So I'm trying to use the consistent notation over here. Okay. All right, so I asked you to go back to the text to verify this, and I hope that's okay now. You get the chance to read it. I mean, it's not something very complicated. You just need to follow the steps, and in particular, because you know that it's going to be a normal posterior, so your goal is to try to find what is the mean and what is the new variance. Okay, so that's what the trick, I think, the textbook was doing. They're trying to use some new expressions of A and B, and then try to use that to express the mean and variance. Yes?
I think I may have misunderstood this when I was reading that textbook. It really looked to me like the derivation was assuming that the likelihood value of theta was the same as the prior value of theta, because it combines those terms. I wasn't sure what the significance of that was.
Oh, okay. Okay, so, all right. In that case, let me actually bring up something that I actually replied to Rachel's comment on Moodle, and I tried to talk about this all together. Yeah, no, don't worry. Like, I think it's actually good to talk about it now. So okay, so earlier we were talking about you have the data to be a normal model, right? Y1 to Yn, they're IID, and then we assume that the mean is sigma, is theta, and variance is sigma squared. Okay, so this is at the data level, okay? And that's a normal. So we also learned so far that the conjugate prior for the mean, so here we want to make inference about the mean. We assume that sigma square is known. And then the conjugate class of this prior is a normal. So this is the second normal that you're gonna see over here. So notice here, this is a prior on the mean. Okay, so on the top at the data model, it's just y given mu and sigma, y given theta and sigma squared, they are IID. So at that level, it's a normal. And in particular, this is fixed. Okay, so in the data model, data given theta, and theta is something that we try to make inference about. Okay, and then because now this theta is random, we want to use Bayesian methods. We start to come up with a class of prior. In particular, we start with the easy case with conjugate prior, and then one class of that is a normal again. So here, the normal, this particular normal, is on theta. Okay, and on theta in particular, we have its mean and variance expressed use a different set of parameters over here. Okay. Oh no, I will keep going. Sorry. Yeah. So here, oops. Yeah. So here you have two separate. We call it hyperparameters because theta is the parameter in the data model, and any of the parameters related to theta, it's hyperparameters. Okay. So here, mu null and tau null zero, tau null square, they're the hyperparameters for theta. And then you can use different values of mu null and tau null square to do your inference. But I really want to emphasize that it's multiple normal distributions over here. Okay? And because the normal prior is conjugate, so you know that the posterior of mean of theta going to be another normal. Okay, and that's what we were trying to show using the textbook. It's mu n and tau n square, and they have their own expressions. It's combined variance and combined mean from the data and the prior. So I just want to tell you that in this particular setting, overall there are three different normals over here. Okay, at the data level, it's the normal data, and then in particular, the variance is fixed. We're only making inference about theta. So that's the data model. And then in order to have a conjugate, nice conjugate results for the mean of the data model of the normal, we put another normal, which is only applied on theta, okay, with hyperparameters mu null and tau null square. And then once you combine all of the terms, so I think Eli's question is, once you combine them, how are you gonna try to recognize what they are, right? So really quick over here, once you have the prior, so here the prior is written in this way, right? And then the likelihood is y1. Over here is also, let me add that up. Also add the sigma square over here, even though sigma square is fixed, but I just put it over here so all of the terms are right consistently. And then yn given theta, sigma square, and pretty much we are also given mu null and tau null square over here, right? And then multiplying this will be what theta, the posterior theta, given your sigma square, your data, and then also mu null and tau null square. Okay, so posterior will be proportional to the prior and the likelihood. And this is a normal, okay? Normal on theta. Okay? This is joint normal on y. Okay? But of course, in order to write out the likelihood, like the density for the joint normal on y1 to yn, you're still going to have theta here and there, right? And that's the terms that you need to collect from the likelihood in order to come up with your posterior. Okay? Yeah, so I would just recommend you just to, if you still a little bit not too sure what, how the derivations are done, go back to the textbook, read carefully, and then if I really see, I guess, the need to just demonstrate how you can do it, I might go back just to write a document to show it step by step, but it's gonna be very much alike to what the textbook is saying. But in class, I do want to point out regarding to Rachel's post as well as Eli's questions, there are multiple normals over here, and that might confuse people. So you really need to think clearly, what is the normal at what level? Okay? So in the past, beta binomial it was less confusing because there are two separate distributions. You have the data to be a binomial, and then you put a beta for the prior, which is the like success probability. And then gamma Poisson, gamma exponential, because they're all separate, it's less confusing, and then it's more straightforward. And also, I guess, because like for beta distributions as well as gamma distributions, we don't know much about it. So we don't even have a feelings about how they behave, right? But once now we move to the normal, because we know about this normal from many other different contexts. And then once you have multiple normals nested together, it might be a little bit confusing, but it's the same story. You always start with the data model, and then now you're given that the conjugate class will be a normal, and then this normal is on theta, and that's a random variable. And then in the end, when you're trying to come up with the conjugate posterior, when you try to derive it, you're going to collect all of the terms that you have from the likelihood about theta, from the prior about theta, and then from the likelihood about theta. And then you combine all of them. And because you're given, you know that's conjugate, so you know that's going to be a normal. And then the textbook was giving you the way to identify, like to help you to identify mean and variance. In this case, it's mu n and tau n squared, which they have their own expressions here and there. Okay? Yes?
Why on number 3 for the posterior is theta not also conditional on
Oh, okay. Sorry, I guess I missed, yeah, I forgot to write the tone notes. They're over here as well. Yeah, sorry about it. Okay, I will update this. So here, so sometimes people like to write about this like conditional, like the hyperparameters, but a lot of times, you know, even if you don't write them, people know that you're conditioning on it. But here, I just want to, because what is this? If you follow it very rigorously, you need to condition on everything that you condition in order to come up with the correct expression for the posterior. So that's why I put the conditions in here and there. But Serena, you're right. I think I missed this tau square over here, a tau no square over here, and I will add that when I get back. Okay, clear? A little bit clearer, hopefully. Yeah. So the more that you will see, I think I will become clearer. But for now, I think it's because of those questions and comments. It's nice to actually stop and talk about how the setup is, and there are multiple normals over here, and you need to make sure that what is for what. All right, so suppose we're good. Suppose we now understand the mean, like the posterior mean and posterior variance. And last time we were actually talking about, okay, a different way to think about the variance is in terms of precision, and precision is 1 over the variance. So if you write this way, this is the variance, you just take inverse 1 over that, and then you will see that, okay, this is my posterior precision, and this, based on the definition that you can get, will be the prior precision, right? And then this will be the precision from the sampling data, okay, from the data model. So based on this, I'm following the notation of the textbook, but the bigger picture, like the more important takeaway over here, is that, okay, look at this. You have the posterior precision equals to the sum of the prior precision and the data precision, or like the sampling precision. And what that tells us in particular is, because all of them are positive, right? So if you know that the posterior precision is the sum of the prior and data, that means the posterior precision is going to be larger than the prior precision, right? Because you add some precision from the data. So think about precision for a little bit. Variance is telling you the variability, the uncertainty, right? So the larger the variance, the higher the uncertainty. Precision is the inverse of that. So the higher the precision, the smaller the variance, meaning that if posterior precision is larger than the prior precision, the posterior variance is going to be smaller than the prior variance, right? So the implication from there, which I actually made as part of my comment to Rachel's question, and I include over here as well, meaning that when you do this Bayesian inference, this procedure, the inference procedure actually going to reduce the uncertainty of your estimate, because you start with your prior, and your prior precision turns out to be smaller than the posterior precision. That means that your prior variance is going to be larger than your prior, your posterior variance. So that means whatever distribution that you come up with. In this case, we're doing a normal case, but in this particular case, you start with larger variance, and then you get more concentrated in your posterior. Which in the past, with the beta binomial and the gamma Poisson, et cetera, I think we have seen similar stories over there. Remember, like, I think with the gamma, with the beta binomial, probably, like, if this is the plot that you can do, remember, like, if you put a uniform prior, right? And then once you combine with the data, you will see a posterior something like this, right? Remember? And then this is the post, this is the prior, and from there, we can also see, yeah, in the prior, the uncertainty is much larger. And then once we combine the data, that reduces our uncertainty about the estimate, which is desired, because whenever you're trying to do inference, not only in the Bayesian methods, but in frequentist methods as well, where we're trying to compare different estimators, we try to reduce, or like try to choose the one with the smallest variance as much as we can. But of course, you also have the bias that you have to worry about. So over there are different set of like theory, but here, the implication of the sum, in this case, the sum of the sum of the prior precision and the data precision gives you the posterior precision, especially once you think about posterior precision is larger than the prior precision. That tells you something about a nice feature of this, of all of this particular procedure that we're doing. Okay. All right, cool. And then from there, last time, we also talked about, okay, not only about the variance, but we also care about the mean, right? So the mean in what we have seen before in this way, and you can rewrite it if you are using the terms of the precision that we defined earlier, okay? So prior mean and sample mean. Okay? So again, we have seen this recurring feature of the posterior mean being a weighted average of the prior mean and the sample mean. Okay, and then again, I think back then, I mean, it's the same plot in some way. Like you have the prior for the beta binomial, and then you have the posterior. So earlier we're concentrating on the uncertainty, how you can shrink the variance, but also for the mean as well, like it's a combined, it's a weighted average of the sample mean and the prior mean. So for the normal case, it's not surprising that you see this as well, but it's easier to see if you put everything in terms of precision over here. Okay, and some other notation and some other ways of thinking about this is, okay, if you define, so this is kappa, okay? If you define kappa null, and in particular, if you define tau null square to be sigma square, so this is given, you just introduce this k null over here. Then if you think of this as the prior observations, like the number of prior observations in some sense, thinking about your like confidence in how strongly you believe in your prior, then you will be able to re-express the mean to be a weighted average again. But here, I mean, it's the same weighted average, but just in terms of, you can think of K null, a kappa null is the number of prior observations, and n is the sample size. Okay, so okay, so maybe let me explain a little bit of what is the prior observation. So obviously we don't have observations for the prior, right? We just have a distribution of the prior. But if you try to introduce a kappa null, let me erase this, it's hard to read. Yeah, if you introduce a kappa null in this way, which is the ratio of, so kappa null is sigma square over tau. So this is the data variance, right? This is the prior variance of our theta. Okay? So if you define this way, you can think of it as, even though you don't know, you don't have like observations of prior, but if I artificially define a kappa null over here, I can think of this as how many observations of prior I can get. And then in a sense that if my kappa null is large, I'm putting a lot of like belief in my prior, and if my kappa null is small, I'm putting not very strong belief in my prior. So, and everything works out in a way that, okay, because if you look at the weights here, if n, we know that n is the sample size, and kappa null will be like the prior size in some way, and then the weights becomes more clear. So for the prior mean, the contribution of prior mean to the posterior mean will be the ratio of the prior size over the sum of the prior size and as well as the data size, right? And then the second term over here, n over a kappa null plus n, will be the sample size of the data over the sum of the prior size and the sample size. So this will be a different way, which might be more intuitive if you think about weighted average. Okay, let me just speak again because people's face looks a little bit confused. Okay, it's really hot in here. Okay, so we're looking at mu null, which is the posterior mean, okay? So earlier we showed that you can show it to be a weighted average in this way. You can go back to verify it, but the weight do not look that intuitive over here. So we're trying to use a different way to express what the weights are. So if you think about it, you know that it's a weighted average of the prior and the data. And we want to express the weights in a way that, okay, I know my priors, I know my data sample size. And if I can also come up with the sample size of prior, and then the weight will make more sense. Say like the total, which is kappa null plus n. This is the total size. Okay, and n is the sample size. And then kappa null is the prior size, if you can define something like that. And that's what we're trying to do. Okay? So if you have the total size to be kappa 0 plus n, and then the sample size to be n, prior size to be kappa 0, then the weight from prior, can you see it? From prior will be kappa null over kappa null plus n, right? And then if you think about the weight from data, that will be n over kappa null plus n, and they sum up to 1. Okay, so this is what we're trying to do, like the motivation of why you want to define something as a prior size, because now that can help you to value or measure your confidence into the prior. And then eventually, if you think about everything in terms of size, then the total will just be the sum. And then the weights will be, say, the weights for the prior will be the contribution from the prior. And the weights for the data will be the contribution from the data. So if you define this way, you see that the weight from the prior mean is kappa 0 over kappa 0 plus n. And then the contribution or the weights from the sample mean will be the sample size n over the sum of these two. Makes more sense a little bit? Okay. All right. Okay. So, right. So these are the implications. So earlier we talked about for variance, it's a, especially in terms of precision, it's going to be posterior precision is the sum of the precisions from the prior and the data. And in particular, posterior precision will be larger, so it's less uncertain. And with that help, we can also define like this prior sample size, and then you will be able to tell the posterior mean is a weighted average. Which one? This? Oh yeah, tau 0. Yeah.
Then, like mentioned in the book, right? The prior distribution is kind of like the distribution of means from the same population.
Mm-hmm.
But in that case, shouldn't the mu be the same as theta because they should have the same mean?
So you're saying that, okay, you're saying that mu, you're talking about theta, right? Which is the mean. Okay, so you're saying that why this is not the same as mu null?
Yeah, if we say that the prior is like distribution of the means.
Right, okay, okay, so this is, okay. So next question is, okay, so because the way that we're defining it, we're trying to come up with the prior sample size. And in particular, we're thinking about kappa 0 copies of prior observations from the same population as data. And we know that the mean of the data is theta. And then if we try to replicate that in terms of the prior, is that what you mean? And then this two should be the same, right? So first of all, let's say this is a random quantity, okay? And this, if you remember, in the prior, theta is a normal centered at mean, mu0, and tau square. So I think that can be some way of, some kind of justification to your comment, because you're trying to. Oh, okay. Oh, okay. So you're saying that, okay, the sample mean is from there. Yeah, I think I need to go back to think about it a little bit more to make sure that like it matches to what the books talk. Okay. So I will go back and then think about it, and then Mudo, I think I will phrase the question again, and then to give you the context, and then talk about this. Yeah. So, all right. Sorry about that. Okay. So so from here we know that the posterior mean will be a weighted average, and that also comes from this definition of prior observation. Okay, so the last part of this is talking about prediction. Okay, so this is, not surprisingly, can be done in two ways. One is Monte Carlo approximation, the way that we used to know. Like if you want to make a new prediction about, like a new prediction of your observation, then if it's, so first of all, the data is a normal model, right? So if I know, if I can sample a new theta, which is the mean from its posterior, which is this, let me write it. Yeah, so first of all, I know the posterior distribution of my mean. If I sample one from that, and then given the mean, the newly sampled mean, and the variance, given the variance, then I can generate a new data point, okay? So that's what we learned from last chapter, and then because it's from the same normal data model, this will be what you're gonna generate, okay? And then you generate a large number of them, and then you can summarize, because that will be your posterior distribution. Okay, so there's one way to do it, and this is Monte Carlo, and this is the one that we actually prefer doing, especially like with the powerful computer. It's really straightforward to do it. But you might be wondering, okay, what if I want to do also to derive it analytically? So remembering the beta binomial, if you derive it, it's gonna be another binomial for the data, for the new prediction. And then for the gamma Poisson, it's gonna be a negative binomial, right? That's what we have seen so far. So in this case, the normal, let's see, yeah, just want to show them all together over here. So if you try to get the analytic solution over here, and there's probably a simpler way that you can think of this. So first of all, we know that this is from the data model, right? We know that, okay, a new draw or a new prediction, or even just the data model itself, given theta and sigma square, are going to be a normal. So this, I just want to bring a different way to think of this. And if you read what's after this double arrow sign, you can think of this, because y, given theta and sigma square, going to be normal centered at theta, and then variance is sigma square. You can actually write y tilde to be sum of two things. One is theta, which is from the posterior. The other one is a random error, okay? Which, if you write it, will just be a normal center at 0, and then variance sigma square. Okay, so let me slow down here a little bit. And I also want to make the connection to the linear regression that you probably know about before. So we're talking about the new draw, y tilde. We know that it's going to be from a normal, and normal centered at mean theta and variance sigma square. Okay, Alternatively, if you define an error term, which is tilde, like epsilon tilde, which will be normal center at 0 mean, and variance the same, sigma squared. If theta is just a new draw over there, you can actually draw epsilon tilde, like a random normal draw from this, and just add whatever theta that you have drawn from its posterior. Does that make sense? Okay. So, so for example, like this is really using the fact, I wrote it over here, using the fact that the sum of independent normal random variables is also a normal. So that's what we remember, like, okay, if you have x is normal, I don't know, mu1, sigma 1 squared, and then if you have y to be normal, mu2, sigma 2 squared, then the sum of x and y, if they're independent, then it's going to be normal mu1 plus mu2, and then sigma square 1 plus sigma square 2. Or sigma 2 square, sorry. Sigma 1 square and sigma 2 square. Okay. So this is really trying to just break it down like a prediction, which is y tilde. If you break it down into theta plus epsilon tilde, then this is going to be its own normal, right? And this tilde, theta itself is from its own posterior. So if you do this, you will notice that, okay, because I recognize this to be the sum, I can actually rewrite or like simplify what is my expectation of the prediction. Because if you do that, so tilde, y tilde is theta plus epsilon tilde, and then because they're independent, there will be the expectation from the posterior plus the expectation from this error term, which is 0, so it's going to just be the expectation from the posterior, right? Posterior mean. And the variance in particular, I think is more interesting over here, is, okay, the variance of y tilde, again, I rewrite y tilde to be theta plus epsilon square, epsilon tilde. And then because they're independent, I break it down. And you see that, okay, this is the posterior variance of theta, right? And this is the variance of the data model, right? And it's known, like we assume that we know what it is, okay? So you see that the variance, so pretty much this is saying that the variance of a newly predicted y equals to posterior variance of theta plus the variance of the data model. So you really have two sources of variance coming into play together when you're trying to make a prediction. Okay, and inevitably it's going to be larger. Let me see what I have over here. Maybe, yeah, sorry, I will just erase part of this. This is hard to read, I guess. Okay, over here. Yeah, it's the same thing that I just wrote, actually. I should have brought the slides together. So if you think about the uncertainty of a prediction, which is the variance, which is the, so this is, yeah, the variance, oh, let's see. The variance of the new prediction is the uncertainty about the new prediction over here, will be the uncertainty about the population center plus how variable the population is, okay? So you see that this will be the sum of these two, okay? Right, so maybe like once you actually do some R coding and then try to make new predictions, you will see that the predicted values will be more variable. And that's why this is, like, that's why it is. So you probably notice like some recurring things that we're trying to do whenever we learn a new model, right? Like okay, especially with the conjugate case, we first of all try to know how to derive things in the correct way, right? That's the first, like, you need to make sure that that works for you. And then pretty much every time we try to look at the posterior mean to be a weighted average of the sample mean and the prior mean. And every time we make it work, right? And then also in particular now with the variance for the normal, if you think about it in terms of precision, that works as well. And that tells you that any of the inference that you're doing is reducing the uncertainty about your estimates. Okay? And over here again, for the prediction, oh, we are trying to look at the prediction for this normal in particular. What's its mean like and what is the variance like? For the mean, it's just going to be coming up from the posterior mean, right? And then for the variance, it's going to be a combined variance from the posterior and from the data model. Okay? So a lot of times, if you say in the future, try to come up with something by yourself, those will be very commonly used key ways to look at how the models are working and whether those are making sense or not. Okay, so just a heads up over here. Okay, so then I came to this slide, which I just talked about earlier, referring to Eli's question, but this, I really just add this slide after I replied to Rachel's comment. And again, 3 different normals over here, don't get them confused, and make sure that you know what is applied on what. And then especially once you try to derive posterior, make sure that you're working on the right quantity, okay? And I have to say that now it's not yet confusing because sigma squared is given. And for the next section, when we move to the point where the normal gonna be a 2-parameter model, sigma squared is random again. And then there are a lot of like derivations here and there. So at least for the simple case now, get it clear that there are 3 normals over here. The data model, the prior is a conjugate normal, and the posterior is a combined normal over there. Okay, all right, so also just a few comments over here. Sigma squared is known, and so we're not making inference about it. And after this, I want you to talk about this particular example that I asked you to read about before class today. So we can look at one way, at least in that example, of how you can come up as a proxy for the sigma square. You assume that you know it. So either you know it from some previous studies, or you're going to use something to approximate that. So again, theta is the mean for the data model, and then theta, because it's random, we're making inference about it, so we use a prior and conjugate as a normal. And then mu null and tau null squared, they're the hyperparameters for the normal prior. Okay, make sure that you know the difference between here the normal is a prior for theta, but here the normal is for the data. Okay, and lastly, we talked about how to interpret the posterior mean, mu null, mu n, and the posterior variance tau n squared, and also in terms of precision and how these things are playing like together. Okay, all right. So I think let's. Okay, cool. So before we move to the next section, if you bring a textbook with you, that would be great. If you can open and turn to page. Just want to talk about that particular example in 5.2. That's the mid-wing length. And I would like to see if any one of you wants to talk about it, but just some background really quick. Here they're having 9 data points. So if you're curious about those data points, it's actually on page 73 on the top. They give you what are the 9 observations are. Okay, then they actually give you the Y bar, and they give you the sample variance, which is 0.017. Okay. So you notice that first of all, because everything you can derive, they're not even using R to answer this question. Right? Because you know that, okay, if I assume that now it's a 1-parameter model, I have my sigma squared to be given, then I only need to make inference about the mean, and then I'm actually having, I put a prior on it, and then I come up with posterior mu n and tau n squared, and then you can actually compute them directly. And then in the end, I have a figure 5.3 to talk about the prior and posterior distributions for the mean. Again, the prior is really flat, very uninformative, and then the posterior is concentrated around, like close to 2, around 1.8 out of this. And then that just completes the entire analysis. But I do want to ask your opinion or like your feedback or like reflection on reading about this example. And then in particular, if you want to comment about how they actually fix sigma squared, that would be great. Okay. So hopefully you spend some time doing this before class today. And if you want, we can also just, you can talk to your neighbors for about 2 minutes and then we can do it together. Of course. I just noticed that.
So basically,
I know.
Right. So that means that it's just as big as they are. Right. So they want sections to expand. And obviously,
Okay, so maybe I will invite whoever wants to talk about it, and in particular, I guess you can describe the problem a little bit, and then comment on how you can, like, what is the way that the textbook example is doing it, and does it make sense? Do you think it's reasonable to make those assumptions? And if you were to do it, would you do it differently, or you would keep doing what they have done? So anyone who wants to talk, that would be great, and I would just hold this close to you.
should be the same.
And Grant, feel free to talk as well if you want. Yeah. Mm-hmm.
Oh yeah. So, but this is the. Yeah, but this graph is famous. This is the. This is what's the smaller? That's fire.
I guess I would say things, yeah, it's one of the reasons we work around.
Yeah, I think it's
Smallest.
it's not. It's easier to do that.
Yeah.
So then it has this that's but what's S?
Anyone?
Do you know what S squared is?
Yeah, they put it out. Okay, so let's maybe talk about S squared first. Maybe like let's answer the last part. So this is the example that they say sigma square is given, right? They assume that they know the variance of the population. And what they did, I think they used the sample variance as approximation to the population variance. So S squared is the sample variance. And they get it, I think, just from the 9 data points. They just, I guess in R is just VAR, and then you get it. So what do you think of using that? Maybe Eli?
Using it for
Like they use sigma square. They use S squared to be the value of sigma square as their assumption. So what do you think of that? Is that a good way to do it, or?
I mean, it's if you have to assume something, it's much better than the prior variance, considering that's like what is it? We have it as like 0.95, which is ridiculously high.
Good point. Yeah, and also like on the plot in the end, like 5.3, you will see that the prior is much more diffused. You have much less, much larger uncertainty over there. And so I guess, yeah, this example actually gives you a way to think about, okay, if you want to do this one parameter normal model, then that means you're fixing the sigma square. And then one way you can fix the value of sigma square is to use the S square. Okay? But just, I mean, maybe not everybody has like thought about it or learned anything about this, but this S square is the sample variance. It's a unbiased estimator of the population variance. And in particular, I want to ask, okay, it's a really small sample size. You only have 9 observations, right? So do you think using S squared is a good estimator at this moment? You only have 9 observations. And use that as approximation to the sigma square. Is there any problem with that? And if there is, what do you think you can do to fix it? So first of all, maybe let me bring up a whiteboard really quick over here. So S squared, by definition, is xi observations, like sample observations, each of the observation minus the sample mean. Take the square, and then because we want to come up with the unbiased estimator, it was dividing by n-1. Okay, and sigma square, so sample variance, population variance. This is defined to be minus mu, and then write it back in. Okay, so this is, I mean, from some previous class, maybe I've taken something like this, maybe not, but I just want to show you that that's how they come up using, and then in particular, it's divided by n-1 in order to have an unbiased estimator. But I want to push you to think, in this case, do you think you're gonna, because the sample size is really small, you're gonna have maybe inflated the variance in some way, right?
Yeah, what I was gonna say is I think it's clearly not a great estimator of the variance because the data is so small. I think it's among the better options that we have. The other thing that popped into my head that I wouldn't know the mechanics of, but would be to maybe do some bootstrapping of some kind. But other than that, yeah, I think it's, we don't want to use anything from our prior because that would sort of be breaking the model.
Sounds good. Yeah, so first of all, if you compare it to the prior, the variance, I mean, it's definitely like a better choice over here. And then because the sample size is too small, there might be other ways you can do it. Eli mentioned bootstrapping, which will be really ideal if you have a really small sample size and then try to come up with good estimator of the variance, and then that will be something that you can do. Okay, awesome. And also just about the example itself, like any comments and then any reflection of the ways that they're doing it. Say if you're given a similar problem, a different data set, but then you're trying to estimate the mean, would you also do what they have or not? What if we want to do bootstrap with this? Oh, sorry, not bootstrap, multi-column approximation. What are you gonna do? I mean, here they give you the analytic solution, right? They give you, you know what the posterior distribution would be. It's a normal with mean something and variance something. So yeah.
I feel like if I was going to do it in my car, I want to actually vary the variance also.
So you're saying that you want to, okay, for bootstrap, for Monte Carlo approximation, you want to change or like make the variance change as well? Okay. Good point. So just based on what we know so far, even if you do Monte Carlo approximation, can you change the variance? Not yet, right? Sounds good. Yeah. So this is actually great. So this is a great preview of what we're gonna do now, because this is the case where, so we talked about like sigma square, and then using S square as the sigma square might have some limitation over there, and then it might make more sense actually to also inference about this sigma square since we don't know about it at all, right? So now, okay, great timing. So we're just gonna move to this unknown mean and variance, and in here I call it as a 2-parameter model, and meaning that, okay, we're still under the, we're still doing the normal model, but now, and it's still the same data model, but now instead of only letting a mu or theta to be random, we are also letting the variance to be random as well, and that's what Eli was saying, that okay, if we have the flexibility to do that, we might be able to get a better estimation over there. So I did prepare some slides. In particular, I wanted to start with an example, but this morning I just thought about it again, and I realized, okay, it's gonna be a lot of derivation involved. So I just wrote up some documents, and this document is on Moodle under the chapter. So this is just a step by step for you to realize what is changing and what is not changing in the model that you're doing. And I don't know how far we can go today in terms of this material, but let's try as much as we can. And again, everything like starting from now is not like in the midterm, so don't feel too stressed out because of the complexity of this particular derivation. So, okay, so Grant, you got it too from Moodle? Okay, all right, so, okay, so let's just maybe don't worry about the slides now. Just look at the handout a little bit. So the 2-parameter normal model is both mean and variance unknown. So, but again, the inference, the data model is still the same, okay? IID, normal, theta, and sigma squared. So if you now make both of them like changing or like uncertain, you want to put prior distribution. So usually, no matter how many parameters you have, we always start to think about from a joint prior distribution, okay? So here, the joint prior distribution will be P, theta, and sigma squared, okay? And, okay, and then, sorry about some typo, just right after there, like in the posterior, I will fix that later. And, but by Bayes' rule, if you start with the joint prior, theta, sigma squared, and then you want to come up with the posterior, which is joint posterior, by the way, theta, sigma squared, given all of the data, then you can actually just apply Bayes' rule. That will be the product of the prior times the likelihood divided by the marginal density of the likelihood, right? All of the y1 to yn. Okay, so this is where we're gonna start. And then So don't, like, keep in mind that's how we're gonna do it. In particular, again, just like in many other analysis that we have done before, we're gonna assume proportionality, okay? The data, the marginal density of the data is somewhere out there, we just don't know what it is, so we won't worry too much about it. But right now, we still need to figure out how to specify a prior for the joint theta and sigma squared. So the particular way that we're gonna cover in this class is to specify a joint distribution as a prior, as a marginal times the conditional. Okay, so this is what you see in the bullet point 3, the first line over there. Joint theta sigma squared becomes the conditional theta given sigma squared times the marginal of sigma squared. Okay, and in particular, the things that you're gonna do is theta given sigma squared gonna be a normal. Okay, so bear with me with the notation at the moment. This is what we're gonna use. And in particular, theta given sigma squared is normal centered at mu null, which is not different from before. We use the same notation. And here, kappa 0 is the same as what we were talking about before. It's the prior size, okay? And notice that for the first normal over there, sigma squared is there, okay? Meaning that we're conditioning on sigma squared, we're having a prior of theta. Okay? Let me actually start writing it a little bit over here, so maybe that's better. So I was saying, if you look at the joint prior, to be conditional sigma, theta given sigma square, and then the marginal of sigma square. And you have two parts, okay? Part 1 is theta given sigma square. It's gonna be normally distributed for the prior, centered at mu 0, and the variance to be sigma square over kappa 0. Okay. So this kappa 0 is prior size. Okay. And this mu null is the same as what we have seen before, okay? But the biggest difference here is back then is just theta. We also write theta given sigma squared, remember? Like in section 5.2, I wrote it, but back then the normal will be mu null and tau null square. Remember? That's what we have done before. Because we're not really conditioning on sigma square itself. Okay? However, back then I wrote conditioning on sigma square just to be consistent, because later when you're doing the derivation, you need it over there to be rigorous. But here, we're trying to specify the joint prior. And here, the joint prior is broken down into a product of two. And the first one is a conditional. And conditional meaning that theta, the prior distribution of theta, is going to be a normal, but also related to the value of sigma square. Okay? So this is a key difference from what we have seen before and what we're doing now. Now it's really conditioning on the value of sigma square. Okay? Meaning that you need to have sigma square. Sigma square is in the prior distribution for theta. Okay? All right, so this is that. And then if you keep reading, the second part will be, okay, so just bear with me with the notation again here. In order to make a conjugate thing that we know before, I'm gonna work with precision. And the precision, which is 1 over sigma square, gonna be a gamma distribution. So let me finish writing here and then explain that a little bit. Okay. So, it just turns out that if you're doing all of the derivation, you will realize that, sorry, let me rewrite this. Yeah, you will realize that in order to have the conjugacy, 1 over sigma square, which is the precision gonna follow a gamma distribution. Okay, so if you're curious about what sigma square itself follows, it's gonna be an inverse gamma distribution. And I will tell you what we're gonna keep using in this particular class. But I just want to show this to you early on, just to show the relationship between those two. Okay, so we're gonna work with precision because that's easier to do, to be honest. Once you start doing it, you realize And then that's 1 over sigma square. And for the conjugacy to work, it's going to be a gamma distribution. Okay. All right, so there's that. And then in those bullet points on the handout, you will see that, okay, mu null is the mean for sigma, which is the mean. And then kappa null is the sample size for that. And then separately, for the prior, for the gamma over here, you will have some extra hyperparameters, right? You will have this nu, this is pronounced as nu 0, and then sigma 0 over here as well, okay? So this nu 0 is the prior sample size for the prior of sigma squared, okay? While the sigma 0 squared is the sample variance of the prior of the 1 over sigma squared. Okay. Sorry, let me just slow down. There are 2 set of priors over here. They all together come up to be the joint prior, okay? And there are some hyperparameters here and there, and in particular, there are 2 in each, okay? So for the prior for theta, which is the mean of the data model, you have mu null to be the hyperprior, which is the mean of the data, and then this kappa null is the sample size for the mean of the data. Okay, that's everything about theta. And on top of that, it's conditioning on sigma squared. And now if you move to the precision or just to the variance, we're using a gamma distribution as the prior for the precision, which is 1 over theta, sigma squared. And then again, there are 2 hyperparameters over here. One is this nu 0, and that is the prior sample size for the prior of the sigma squared. While the sigma 0 squared is the sample variance of the prior of the sigma squared. Okay, so just to be careful, there are 2 separate priors over here, and then the hyperparameters are working like separately. Okay, when we're talking, so you can always say, oh, like, okay, I have some prior sample size, but kappa 0 is prior sample size for the mean, while nu 0 is the prior sample size for the sigma squared. Okay, just to differentiate early on, because we're really doing 2 sets of things over here. All right, so if all of that is okay, then what comes to the real hard work part is how to derive the posterior. So I posted like on the handout, you notice that I wrote down some ideas here and there. And what I'm hoping is this just some ideas you can try, and I give you what the answer is over there. And for the rest of today, as well as like any other time before the actual class on Wednesday, because Monday will be a review, but Wednesday we're gonna pick up from here. I want you to do derivation in particular from page 2. You go back to the second page. I wrote over there, okay, instead of working with 1 over sigma squared, which is the precision, let's actually define the precision, which is phi. Okay, phi equals to 1 over sigma squared. So instead of working with theta and sigma squared, you're gonna work with theta and phi, okay? And phi itself gonna be the gamma that we just talked about before over here, okay? With nu 0 and sigma 0 here and there. And I use some new notation over there, so just stick to those notation, because in the end, you will see that why people use that notation instead of like the more complicated ways over here, okay? So I would suggest, I mean, we only have like about 5 minutes left today anyway. So you can start like sketching a little bit, starting from like this page 2, because I wrote for you what are the priors. I wrote the gamma prior for phi, and I also wrote the normal prior for theta, given phi. And you notice that I started using proportional signs here and there. Okay, so don't worry about the normalizing constants. But I left the normal likelihood for you, because I think it's a good exercise for you to start doing precision instead of variance here and there, okay? And then once you do the normal likelihood, once you finish that, you can start deriving what the posterior is. It's gonna be some work, and I think the plan is for you to do it separately, and then I will also assign people on teams, and then maybe you can talk about it before the class on Wednesday, when we come back again to talk about the new material. Okay, So yeah, feel free if you want to start now. Feel free, and then also in terms of like the team assignment, I think I will either just assign it or like I can post like 4 different teams and you can sign up based on your preference. That's fine as well. But I really, again, now I want to take the chance as well. Like whatever, like I was trying to assign before the class, like as a team or even just individually. I think it will be good that you do some review and preview before the actual lecture when we talked about those. Because again, otherwise you're gonna get lost and then you're gonna just keep getting lost for a longer time. But if you just do a little bit of preview, I think that would help a lot. And I will try to direct as much as I can into the material that I think is the most relevant to what we're gonna talk about, okay? So if you want to go early, that's fine as well. But and if you want to just keep this aside until like the midterm is over, that's totally fine as well. And this is not included in the midterm, and everything before this is. So make sure that you know the scope. I will send an email about this as well, about the scope, about information about the midterm, and also 2 different choices for maybe let me ask now, like if I'm gonna post 2 different choices for you to do the take home, do you have like preference of time? Because what I was thinking is, everybody should have about like 24 hours to do it. It's not that long. It won't take 24 hours, of course, but you have other things that you need to do as well. So one option I'm thinking is, if you finish the written part on Monday evening and you just take it, for example, like at 9 p.m., then you should send it to me, like your result or like your take home part through email. I prefer PDF through email by like 11:59 on Tuesday. So that's one option. But what about the other ones? If you want to have another one, I don't know. If you have preference, say, do you want to do Monday? I don't know, like Monday from 10 early, like morning, like Monday, 10 a.m. Monday to 10 a.m. Tuesday. If any of you have, I mean, again, because the midterm is on Monday night, I guess you probably don't want to do the take home at that time. But if any of you have any other options or like preferences, let me know. Otherwise, I would just stick to, you pick it up from the take home, you pick up the take home from the written exam after you've done it, and then you have about 24 hours to finish that and email me your write-up. Okay? Yeah, if not, I will just make that as the only option. But if you want anything else, just talk to me. I just need to be fair to everyone to have 24 hours. Yeah, the midterm is gonna be Rocky 300. Yeah, and I'm like my other class is taking the midterm at the same time, so it's just gonna be big room, lots of people, but should be okay. I don't think it's gonna affect any others. Yeah, so the midterm, I booked the room from 6 to 9 on Monday, and I think you should just budget about like an hour and a half for yourself. But again, so you can come at 6, you can come at 6:30 anytime, but at least give yourself an hour and a half to come. But if you come at 6, you can leave by 9. I don't mind if you want to take longer time to do it. That's fine as well. So all of this I will email, and it should be okay. All right? Okay, thank you.